Okay, we're still working through 1.1, and in this video we're going to talk about piecewise defined functions, or as we'll often say, just piecewise functions. So we're going to identify, apply, and analyze them. But first, what are piecewise functions? So let's define them. We say f, a function with domain A and range B, is piecewise defined if f has different rules for different subsets of its domain. So we can say is made up of different rules. And so we'll often express this like this. So we say f of x equals, and then there's a choice. It's not really a choice, but it's a choice in the sense that depending on what x is, where it lies in its domain, if x is in some subset of A, or something else if it's in the rest of A. So this is not very precise terminology, but you'll see what I mean in a second. And so if you can imagine abstractly that this is the domain A, some part of it is some subset that we'll call it S. And so depending on whether x is in here or in here, we'll have different rules. So some quintessential examples here, right? So what you want to keep in mind is, or what we'll call the prototype for this kind of function, is absolute value. So the absolute value function, which we call bars containing x, is actually defined piecewise as x if x is greater than or equal to 0, and negative x if x is less than 0. So we have two different rules depending on what side of the x-axis we're on. So if we're on the right side of 0, right? So this is the positive side. Then we just take x as is. So for instance, the absolute value of 3 is just 3. On the other hand, on the negative side, so left of 0, say -2, the absolute value of -2 is just 2. So we take its opposite sign. But every point here, every x value allowable, which is all real numbers, has one and only y value associated to it. So it's still well defined. And we can generalize absolute value, actually, by thinking about any function of x. If we apply the absolute value of that, what we mean is f of x if f of x is greater than or equal to 0. So the y value is greater than or equal to 0. And negative f of x if f of x is less than 0. Let's see what that means practically. So example 1. Let's graph the function y equals the absolute value of x minus 1 cubed plus 2. Okay, so this is a function where we have some polynomial expression and then we take the absolute value. So what we want to think about is, where is this this part of the function, where is this positive? When is it negative? Okay, so in other words, let's set it equal to 0 and solve the equation. So to find a partition of the domain, so we agree that the domain of this function is the entire real line. It's all real numbers. But at some point, we're going to need to define a new rule for it. And so that's the point where we're going to split the domain. So we're going to set y equal to 0, which means x minus 1 cubed plus 2 equals 0, which means x minus 1 cubed equals negative 2. So x minus 1 equals the cube root of negative 2. Remember, you can take the cube root of a negative number, so that just means it gets pulled out. And then lastly, x is 1 minus the cube root of 2, which is roughly negative 0.26. So this means our actual function, if we want to express it in a way that we can graph it, we'll be looking at left of negative 0.26 and right of negative 0.26. So where is it positive? Where is it negative? In order to figure that out, we can take a test point. So for instance, let's plug in 1. So if x equals 1, then y equals absolute value of, well, 1 minus 1 is 0, so 0 plus 2. And what's inside the absolute values is already positive. So that means on the right side of this value, 1 minus cube root of 2, this function is positive, and on the left side it's negative. And in fact, let me draw this real quick so that we understand what we're talking about. So we got 1 minus cube root of 2, and we just said if we pick 1, then it's going to be positive. And if we pick something on the left side of that, that's going to be negative. Meaning that this mirrors when we're talking about when an absolute value function is positive or negative. Remember that this tells us where to make our changes to the function statement. So now we can say y equals, and if x is something that makes the function positive inside the absolute value bars, in other words, if x is in 1 negative root 3 over 2 to infinity, actually we can plug in that value, we can make that a bracket, then it is just that expression. So x minus 1 cubed plus 2. On the other hand, we make it negative for the other section. In other words, if x is in negative infinity to 1 minus root 3 of 2. So this means we graph our function, and this is just a shifted, or ordinarily it would just be a shifted cubic function. So what this looks like ordinarily without thinking about the absolute value, we have a point 1, 2, and it should look like this. Except here, this point right here, 1 minus cube root of 2, means that this function is now below the x-axis, right? That tracks with what we said, if x is less than 1 minus root 3 over 2. So we're in fact going to actually mirror it across the x-axis. In other words, our actual function looks like this. So we ended up with the same graph, but there's a reflection point where it changes from negative to positive. Okay. Some other examples of piecewise defined functions include something called the Heaviside function. Very ubiquitous in the sciences. You can think of it kind of like a light switch. So it's defined as h of t is 0 when t is less than 0, and 1 when t is greater than or equal to 0. What that graph looks like then, here's one. So as long as you have a negative t value, the function value is 0. So the y value is 0. And then when you reach t equals 0, you step up to y equals 1. And then continue along that track forever. So that's the Heaviside function. So you'll notice that there's a step here. That's an important word. A step. And every t value, so the t represents time typically. Every t value has a corresponding y value and only one corresponding y value. So in other words, what is h of 0? There's no ambiguity here. 0 is in this part of the function, so that means h of 0 equals 1. All right, so some other practical applications of piecewise defined functions include something called plugging a hole. What do we mean by that? So to illustrate this, let's consider the function y equals x squared minus x over x minus 1. Okay, so when we try to simplify this expression, or this rational expression on the right, we can recognize that if we factor out x, this function actually turns into this, right? So the numerator is x times x minus 1, and the denominator is x minus 1. Typically, when we're working with this algebraically, we would say we can just cancel those, but we can't here. Why is that? So this function is interesting in that this function has a hole at x equals 1. So in other words, x equals 1 is not part of the domain. Oh boy. Jesus Christ. I hate when that happens. Stop. So it's not part of the domain, but it's also not a vertical asymptote. Unfortunately, when you go to graph this in Desmos, it won't show you that the that there is a hole, it'll just show you a continuous function. I'm using a word, unfortunately, that we have to define more precisely later on. So the domain here is, in fact, negative infinity to 1 union 1 to infinity. Hence why we call it a hole, right? You just punch out a hole there. But at x equals 1, what would have been the value, right? We would have had y equals x times x minus 1 over x minus 1. And if we can assume that we just cancel those, right? And that's just x, right? So we would have wanted, so to plug the hole, define y equal to 1 when x equals to 1. Does that make sense? Because otherwise, remember that if x is not equal to 1, you can just cancel those expressions and you just have the expression y equals x. So in other words, the full graph of this function would just be the line y equals x, except exactly at 0 you have a hole, and we can define a new function that plugs that hole. And we define that as f of x equals the original function expression, which is x squared minus x over x minus 1, if x is not equal to 1. So this tracks, the first line tracks exactly with what we had originally. And if x equals to 1, we ignore that other part and we just define it equal to 1. So that plugs the hole. All right, so that's enough about that. Now, let's have you try it. So here, your task is to write the function definition. In other words, as a piecewise defined function with the bracket and the different lines for different parts of the domain. For the f in the graph below. Okay, so here I'm going to have to be very precise so that you can see from the picture alone what this function is. Okay, so here's 1, 2, 3, 1, 2, 3, negative 1, negative 2, negative 3, negative 1, negative 2, negative 3. All right, so this function passes through the points negative 1, 0, 1, 0, and 0, 1. Also passes through the points negative 2, negative 2, and 2, negative 2. Whoops, that's not right. So from this part to this part, we're looking at a straight line. From this part to this part, we have a semicircle. Okay. And from this part to this part, we've got a line again. So three distinct parts of the domain. So your answer should look something like this. You're going to have a first, second, and a third, corresponding to the first one corresponding to, let's call this 1, this one 2, this one 3. First one corresponding to this part, the second one corresponding to this part, and the third one corresponding to this part. Okay, now I'll even use different colors if you'd like. So you can clearly see the different parts here. And you can be creative, remember. The only part that matters is make sure there's no overlap, okay? So you can decide which part contains the endpoints. There's that part right here. There we go. All right, so give that a shot.